Hi class, we are starting the next chapter, chapter 2, where we discuss everything about limits. We're going to start off by talking about the easiest way of finding limits, which is a numerical method, as well as analyzing the graph of a function. So far in this class, we've talked a lot about, not a lot, but every so often I'll say, what is our function doing as x approaches this value, right? Or what is the rate of change as the interval that we're looking at is getting smaller, right? We had a problem that was similar to that. Or I might say, what is our function doing when x gets really, really large or gets really, really negative? Okay, so all of those have to do with the idea of limits. So if you've already seen the pre-calc material, I discussed limits in there specifically in numerous places. So for those of you who have seen that material already, this should also be a review. We will touch on a lot of new stuff in this chapter, and chapter 3 is really where we start to have like new stuff, right? So let's go ahead and talk about limits, right? So when we're talking about limits, what we're doing is really as I said before, we're discussing what our function is doing. What is the output of our function doing as our inputs approach a value, right? So as x gets really, really close to, let's say, 5, right? So it would be, what is my function doing at 0? What's my function doing at 3? What's my function doing at 4? At 4.5? At 4.9? At 4.99999? As I get closer and closer and closer to 5, what are the outputs of my function doing? That's what I'm interested in, okay? So we call this a limit, right? My function is approaching a value as my inputs are approaching a value. And the outputs that my function approaches is called the limit, okay? So my function goes to a value, which we'll call L for limit, as my x values come close to a value as well, okay? So we call this the limit of f of x as x approaches the value c. The notation for that is this. The limit of f of x as x goes to c is L. That's how we say that. Okay, one more time. The limit of my function as x approaches this value is equal to the value L. Okay, so what we're doing is we're looking at what our function is doing as we approach, input-wise, the value of c from the left side and from the right side. So we're looking at what x is doing when it's less than c, but moving closer to it. And we look at what x is doing when it's larger than c, but moving closer to it, okay? So we call this moving from the negative direction and moving from the positive direction. So when I move from the left, right, when I'm coming from the negative side or from values that are less than c, this is called a left-hand limit. It's the limit of my function as x approaches c from the left, or from the negative, or from the values that are less than c. Those are all equivalent ways of saying the same thing, okay? And we talk about what my limit is doing as I approach from the right side, or from the positive side, or from the values that are larger than c. So I will have a plus here when I'm coming from the positive direction, from the values that are larger than c. As a graph, you can represent it like this. I'm looking at the inputs as I come from the negative side, or the values that are less than c. That's why we have a negative, right? Less than, smaller than, not even smaller, just less than, right? Values that are approaching from the negative direction, okay? From the left, I'm coming from the left. Coming from the right, or the positive direction, or the values that are larger, is my right hand limit, because I'm coming from the right, coming from the left. So as I approach c, my output values are approaching this value of L, right? My output here, my outputs are getting a little closer and closer and closer to this value as my inputs are approaching this value, right? Same thing here. As I approach in this direction, my outputs are getting closer and closer and closer and closer and closer to this value L. So as I approach C from either direction, I'm either approaching L from here, if I'm coming from the left. If I'm coming from the right, in this case, my outputs are coming closer to L from this way. So my outputs are squeezing towards L, my inputs are squeezing towards C. Okay, so that's how we kind of read a graph in order to figure out what the limits are going to be via the graph, right? So if the limit of a function as I approach a value from the left is equal to the same limit as I approach that same value from the right, then my limit exists. Okay, so if the left limit and the right limit both go to the same value, then I can say that my limit of my function as I go to C is that value L that they both agree to. So what that means is that the left and right limits both have to agree and go to the same value. If they don't go to the same value, then my limit does not exist. Okay, so if my limit as I go to the left is not the same value as the limit as I come from the right, then I do not have a limit at that value, right? That input value, the limit does not exist for that function. Okay, so one of the ways that we need that we find the limit at a point, besides looking at a graph, right? Sometimes we can look at a graph and we might not know what this value of L is just by looking at the graph. So one way that we find these values is using numerical methods. So the numerical method is to plug in values closer and closer and closer to C from the left and from the right and see if they agree. And not only that they agree, but they come close to approaching the same value. Okay, so this is our first numerical method. So let's go ahead and look at an example. Okay, so let's look at the function sine of absolute value of x divided by x when we are next to the value of 0. Okay, so what we're going to do is we're going to plug in values that get closer and closer and closer to 0 from the left or from the negative side, and we'll plug in values closer and closer to 0 from the positive side. Okay, and we'll look at their outputs. So if I plug in 1, so this should indicate to us that we're coming from the positive side because this is larger than 0. So as I approach from the positive side, that means my values will get smaller and smaller and smaller closer to 0, right? So when I plug in 1, I get 0.845. If I plug in 0.1, which is a lot less than 1, much closer to 0, right? I'm at 1/10. I get 0.9983. If I plug in 1/100th, I get 0.99983. Okay, if I plug in 1/1000th, I'm even closer to a value, right? So if you can see, it kind of looks like I'm approaching the value of 1. This is pretty far from 1. This is really close, very close to 1. This is extremely close to 1, right? If I plug in, and that's it. So if I plugged in even more zeros, like 0.000000001, I would get 0.9999999999983, right? So the closer I get to 0, the closer and closer I'm getting to 1. I'll never actually equal 1 until I possibly plug in 0. Okay, so as I come from the negative side, so now I have a -1, so now I'm starting below 0, and I'll start to plug in larger values and approach 0 from the left hand side. Okay, so I plug in -0.1, I get the same value but negative. Okay, same value as before but negative. So I'm approaching an output value of -1 when I'm approaching from the negative side. So as I approach -1, and as I approach from the positive side, okay, from the positive direction, so larger and then getting smaller, closer to my value, I approach a value of 1. So my two limits do not agree with each other. The left side limit and the right side limit are not equal to the same value. Okay, so what that means then is that my limit as I approach 0 does not exist because the two different sides do not agree with each other, right? So let's kind of look at this graph real fast and we'll see what we mean. Okay, here looking at the decimals graph, it's very easy to see that the left side goes to -1, the positive side goes to 1, okay? And at that value, right, at 0 it's undefined because 0 is an asymptote. So I couldn't just plug in 0 here and say, oh, what do I equal? Because I actually have a vertical asymptote at 0. It does not exist, right? So I couldn't just be like, oh, this is my value, because it doesn't work that way. The left side limit, the right side limit, they don't agree. One goes to -0, right? So if you can see what my outputs are doing as I come across. So my outputs as I approach 0 are getting closer and closer to -1, right? I'm getting closer to -1, very, very close. and then all of a sudden it's going to say it's almost -1, and then it goes undefined. Okay, well actually here it's saying it's defined, but so the reason it says -1 is because I'm so close that the system can't differentiate between it, and it's just going ahead and rounding up for us. But I guarantee you, if you plug in -0.02, you are not going to get out -1. Actually, we saw that already. We plugged in 0.001 and we got something very, very close, right? We got 0.999999983. So this is just a decimal system rounding up. So again, that's why I say watch out for round off errors, because when you plug in -0.02, we know that it is not -1. We know it's 0.9999983. Okay. Same thing as I come here from the right and I approach, you can see my output values are getting larger and larger and larger. They also are approaching a +1. Okay. And again, we have a round off error here. And so it's actually undefined at 0. Okay. So as you see, we're so close to 1 that Desmos just rounds it up, right? We're so close to -1 that Desmos just rounded it down to -1. So now let's take the following graph. Got a couple of values, left and right limits, limits at single values, and see what we're approaching. Okay, so looking at the graph above, we know that as we approach -4, for instance, from the left, okay, so as we come this direction, this is what our outputs are doing. We're approaching a value of 2 as I come from the left as I'm getting to -4, right? So -4, the superscript negative here means I'm coming from the left side. Okay. As I approach from the right side, I'm approaching, my outputs are doing this. They're decreasing towards 0. So from the left, they're coming to 2. From the right, the outputs are going to 0. So the outputs of the two sides, as I'm coming from one side to the other, do not agree. So my limit at -4 does not exist. Okay. Notice as we look at +2, okay, as I come from the left, right, as my inputs come this way towards 2, my outputs are coming and getting closer and closer to 4 as I get closer and closer to 2. As I come from the right, okay, as I plug in values coming this way, my outputs get closer and closer and closer to 4 as well. So both of those limits agree. So as I come from the left, I come to 4. As I come from the right, I also come to 4. So the limit at 2 is 4, since the left side and right side agree. Okay, and we can look at plenty of other places here, right? Just like, let's say 1, as I come from the left towards 1, and as I come from the right towards 1, both of those values come to the value of 1. So my limit of my function as x goes to 1 is 1, since the left and right side both go to those values.